Okay, so we're doing Taylor expansions. There were no homeworks for that yet. So the homework was just for the couple from the delta function. Is that enough for the week? Why not? I have a couple for the Taylor rule. Okay, so let's do multivariable Taylor expansion again. But we're going to start with one variable, because this is the one we really have to know and love. Okay? And I'm just going to go up to second order. And instead of f prime, I'll write df dx. df dx evaluated at x naught, x minus x naught. Okay. So that's your first and linear approximation. Then you've got a half, second derivative. Very important that you evaluate them, at that point of analysis, x minus x naught squared. Other thing, when you do an expansion and you've got this x minus x naught squared, you don't make the mistake of expanding it out again. Okay? We want this just as that small quantity, plus and so on. Okay? And the picture that goes with this, and actually goes with both of them, is that out of x naught, our function's doing something. It could be a local minimum, maximum, could be something else. And, well, the one I just chose has a derivative equal to 0 there. But good. So x, y equals f of x. So now what about the general n greater than 1? So now we're looking at the vector x. Okay, so we've got x1 to xn. And if it's x1 and x2, we can often just do x and y as well, okay? But, so now we had scalar function at this point x in n space, f of x0, then the linear approximation was the sum of the partials with respect to x of I, all evaluated at that point. So this is a collection of constants, I equals 1 to n, and then x minus, so xi minus x0i. And this is obtained by implementing the chain rule. So the linearity of this thing is due to the chain rule coming out of linearity, but we're going to study linear algebra soon, and then we'll come back and do the proof of the chain rule. So this came out of the chain rule, and repeated application of the chain rule kept bringing you another sum. So we really had a df dxj, actually, I'll write it out first. Ij evaluated at x0, then you've got xi minus x0i, xj minus x0j. So it's just bookkeeping, and you can't allow yourself to be intimidated by this bookkeeping here. We really did the same thing we did on this one when we were generating this expression to the first derivatives, and since the first derivatives were already there, we did a summation, and we were doing all the mixed partial second derivatives, okay? And then we saw that this can be thought of as a gradient of f at x0 dot product with a vector x minus x0. Because it was just the first times the first, second times the second, and so forth, okay? This one has a similar interpretation. If you take the sum over j and these jth ones, so the order, switch the order of these. You could be looking at this as, you know, ij, just a matrix. We didn't start with a matrix, but we've generated n times n terms, Fij, delta xi, delta xj. Where the Fij's were just evaluated at the x0, taken as these mixed portions here. So we need to just do a couple of examples, and our examples are going to be mostly of two variables, and I'll assign a couple of problems for you guys to do. Okay, and then we have critical point. When all of these first partial derivatives equal 0 for all I above. Here's a symbol for there we go. Like that. And local max or min, we have to define something called the Hessian matrix. So Hessian matrix Fij equals d squared f dxi dxj, and we'll evaluate it at this point x0. So this now defines an n by n matrix. I could put the x0 here as well, because in terms of your function, these are all constants now. They can contain all kinds of parameters. They're all constants. And it's the nature of this matrix, and we had that as the last thing we wrote down. It tells us whether or not we have a local minimum, maximum, or neither. Okay. So the thing to do is just look at an example now. Once we've seen this structure here, we just have to go back to the most basic example. A couple of the most basic examples. So I'm going to go to, okay, we'll use x1 and x2. F of x1 and x2 is equal to some constant plus b x1 squared plus c x2 squared. Have you seen in their mind's eye what we have here? Depends on the values of a and b. But this is the first and last one that we can graph. So we've got x1 and x2. At the origin, it's equal to a, and depending on the values of b and c, you can do a number of things, but let's just say it's like a paraboloid. B and c are positive. So let's look at what our formalism tells us. So we're going to look at df dx1, which is 2bx1, and df dx2 is 2c x2. Okay, so a, b, and c are constants. So where is, if we're just doing this analytical work, where's the critical point? We need both of these to be equal to 0. So at x1 and x2 both equal to 0. So equals 0 when x1 equals 0, x2 equals 0. So we need both of them to be 0, and then we have a critical point. the Hessian matrix, I will do d squared f dxi dxj. That's going to be a 2 by 2 matrix. And the second derivative with respect to x1 is just 2b. The second derivative, or the mixed derivatives, d squared f dx1 dx2, they're both 0. And then the second derivative with respect to x2 is 2c. So now we have a couple of cases. Okay, now I won't write down this criterion for the Hessian matrix. This has to be in our notes. So put this for the positive definite. So f ij is positive definite if determinant of f11 f1k fk1 fkk is greater than 0, k equals 1 to n. I should actually say k equals 0 to n. K equals 1. Okay, if k equals 1, it's just actually the corner. Okay, it's not. So we'll do it this way. So what determinants are these, by the way? You can visualize them, they're just the corners, the upper corners. So suppose we have f11, f12, f1n, f21, f22, etc., down to fn1, fnn. So what we're looking at are these determinants. This one, if this is greater than 0, and then if this one, and then all the way out to that. So those determinants taking us down to the left corner, okay, all the way out. If they're all greater than 0, then the matrix is positive definite. If not, it's not. Okay. So you need that in order to have a local minimum. So then x0, a local min. Okay. Like I said before, in physics applications, we're often doing a construction where we already know it's positive definite. Okay. But in this case, we've left it up in the air. So what about this matrix here? It depends on the values of B and C. So if B and C are both positive, then yeah, then those two determinants are both positive. But suppose B is positive, or suppose B and C are both negative. Then instead of a bowl, you have a mountain. Okay, so then it's a local maximum. And what if B is positive and C is negative? Okay. Then you've got a saddle. Your math books will draw some potato chip looking saddle, but I can't do that. But you guys know that. So yeah, this very simple example already contains enough of the criteria to illustrate those concepts. I'm going to bring out a couple of homework problems that you guys can put in your notes as well. So yeah, this is the basic process. As soon as you have non-trivial functions, it turns into work to find, say, the minimum, because you have to satisfy a bunch of equations. However, I have a couple medium grade ones that we'll put up here as homework. Here, I'm just asking for the critical points. And, you know, you locate them and then say, what are they, right? Local minimum, min, max, cell, question mark. And the second example we're gonna study would be F, this time I'll use X and Y. X minus Y, X plus Y. This is a great example because it's hard to visualize what's going on here. And what we're going to do is expand to second order. Expand to second order at X, Y equals 1, 1. That's a point that's safely away from any pathological problems. And we want to expand it to second order. So when you do that, remember that you're going to be having terms like, just generate all of them. You know, you'll have, say, E, F, E, X1 at 1, 1. That'll be a constant. And then you'll have X1, 1. No, I'm using X and Y, sorry. You'll have df dx, X minus 1. You'll have something like d squared f dx dy at 1, 1. So that expression, you'll have to take the two derivatives, evaluating them 1, 1. And then when you write this out, it's going to be an X minus 1, Y minus 1. Okay. Never multiply these out again. Okay, then you just have a nightmare. You're looking at, and same if you had the d squared f dx squared at 1, 1, you'd multiply that by X minus 1 quantity squared. Yeah, the warning about not multiplying it out because I've seen it done, right? So you just leave it in that form. You have that constant, then X minus 1 squared. And then you'll actually be able to see the structure of what's going on. These four derivatives, you know, they form a matrix. And you can see what's going on in each direction around the point 1, 1. Of course, the value of f itself at x, y equals 1, 1 is 0. So anyway, yeah.
Is due tomorrow or next week?
How many do we have due tomorrow before this?
Like 4 or 5.
Are they all really easy? We can do these next week. Put these in next week. Yeah. New topic. So next week. So Monday's off, but that doesn't affect this class. So we have Tuesday and Thursday, and then the following Tuesday we have an exam. That's the week before the spring break. So we'll take the exam on Tuesday. So Thursday we can do some review. Next week I'll get all your homework back to you. We'll do a big review. And then see where we stand. Good, so this is the section on multivariable Taylor expansion. And we'll do more with them as needed, okay? But you definitely want to see that structure because we're headed into the linear algebra section of the semester. And before we do that, we just have to review, you know, vectors in 3 dimensions, and vectors in n dimensions, and then vectors in complex spaces, and then function spaces. So we kind of have to build it up systematically. So the rest of today, I think, is mostly review. Let me see. Here for us. So the whole vector space concepts, they generalize. And then a lot of the stuff we've done early in the semester finds its place in those applications. I'm just gonna get started with the vector review. Good. So we've been using vectors, we just want to become a little more systematic with the whole thing. Okay, good. So first vectors, first run through these vectors and vector spaces. So the first version is that vectors are arrows. Okay, they're just arrows, and those are the ones we've been looking at for the most part. Vectors are just arrows in free space. So those are the ones we'll review first, okay? So we have vector, for example, we could have the position vector x, y, z, and then we could put it in an orthogonal system because we're already used to that, x, I hat, y, j hat, z, k hat. And then we have the addition of vectors and subtraction and so forth, you know. A plus b is again a vector, and the subtraction a plus negative b. So then we have to be able to take a vector and its negative and multiplication by a scalar and all those properties. Okay. We're going to list them all formally, but we actually just want to go through with some of these things as we use them all the time. So we have the laws of vector addition, and then we get the scalar product, or let's go first for the magnitude of A, and we often just leave the arrow off, define it as that, and then we have to know about the components. There's 1, 2, and 3, A1 squared plus A3 squared. And from there, we learned about the scalar product that I've brought into play a few times already. So then we would have to know about the magnitude already, and then this dot product we can define as A1, B1 plus A2, B2 plus A3, B3. And if you define it like that, then you could show that this is equal to the magnitude, product of the magnitudes times the cosine of the angle between A and B. So that's actually a good little exercise. So suppose I define it this way, and then I can say, prove this for homework. Prove this, okay? Homework. So given this here, you want to prove this. And you could, without loss of generality, you could restrict to a plane. Say the two vectors span a plane. So you can restrict it to a two-dimensional case, and once you do that, the trig will just fall right into your lap, okay? So I'll just put this as a note. The two-dimensional case. So yeah, once you have this, then you can have the magnitude of A as the square, so I'll actually have to put the magnitude signs here, as the square root of the vector dotted into itself. Right. And then, for example, in mechanics, I often use a vector squared just as common nomenclature as the dot product of the vector itself. Okay. Good, so you have that, and what else do we need here? We usually also know about the vector product. So now we have, and we're still in free space, A cross B, and we're going to define it we're going to define it in terms of this determinant rule, A1, A2, A3, B1, B2, B3. And if we write this out, we're making use of the fact that I hat, J hat, K hat form a right-hand orthogonal system. Those are the ingredients we have when we do vectors as arrows. So we're going to extract the basics for this. The next question is, what about vectors in n space? So this was in 3 space. These are the ones we have full intuition for. Actually, so this is a good homework problem, right? There's another interesting one that we want to be aware of here in free space. And that is we can do interesting geometry problems with vectors. Say you wanted to know the angles between the different parallel diagonals through a geometrical object, like even a cube. I'm going to put this as a homework as well, just to get the ball rolling on these. So suppose you have a unit cube. And you want to find the angle between a diagonal across the entire cube and one of these verticals. So this diagonal goes here, right, from one corner to opposite corner, and this is just up one side. So what is this angle equal to? Not one we know off the top of our head, unless maybe someone does. But you can get these types of angles just by setting up some vectors and working out the scalar products, okay? Working out the lengths of the sides and then the scalar products. So find theta using vectors and scalar product. Right, so that's the first go around through the vectors, and that's all just review. So we did the multivariable expansion, so we definitely have to generalize these things to n dimensions, and we'll do that with the exception of this guy right here. So these all generalize immediately to n dimensions. So this was vectors in 3 space, so the next part is vectors n-dimensional real vectors. Okay. And we're going to find actually all of these same rules, so now A equals, we can have an ordered n tuple, 1 and A sub n. Or we can have A is equal to the sum over A sub I, and then I have to have some kind of unit vector designation, say E sub I hat. I equals 1 to n. And I'm going to have the E sub I hat dotted E sub j hat equals delta ij. So I'm going to have unit orthogonal vectors. And that's no problem, because E sub I hat, if that's, or just 1, E sub 1 hat is 1 with a bunch of zeros. E sub 2 hat is 0, 1, bunch of zeros, etc. They're unit vectors. And the scalar product is done exactly the same way here. So A dot B is equal to sum over A sub I, B sub I equals 1 to n. Same for the magnitude and same for the dot product, and you can actually define an angle between n-dimensional vectors by utilizing that second definition as well. A sub I, I'll put a note here with these. If you want to do A dot B, you could say it would be the sum of A sub I, E sub I hat, and then you'd be doing the dot product with the sum over B. You're not going to repeat that subscript, you're going to choose another one, say K, E sub K hat. And then when you do this double sum over I, sum over K, you get A sub I, E sub I hat, B sub K, E sub K hat. We'll do one more step here. A sub I, B sub K, E sub I hat, E sub K hat. And this is where we have I, K, A sub I, B sub K, and this Kronecker delta, which was delta I, K. It's 0 unless I is equal to K, and then you can just choose one. I, A sub I, B sub I, which is what we have down here. So yeah, generalization to n components, no problem either. So what about when you have a vector space, n-dimensional complex vectors? Have you guys seen that one before? N-dimensional complex vectors, how about you guys? No? this one so far so good? Yeah. So the complex numbers, as we learned them, they have all the properties of numbers except there's one thing we have to take into account. Yeah. Okay. So complex, so n-dimensional complex vectors. There, the problem is the following. You want to have the magnitude of a complex vector, you want that to be real. Okay. But the scalar product, a sub I squared for complex numbers is not necessarily real, right? You want this to be real and positive. Should be real and positive. So what we have to do is modify that definition and retain the real case as a special case. So what we do is let A dot B, we're still using the dot form, equal the sum of A sub I, B sub I, complex conjugate. And we can also complex conjugate the first one instead of the second one. This is going to do the trick. So I'll write this and retain, you know, your E sub I hat is equal to, or your E sub 1 hat equals 1, 0, etc. Okay? So you're going to retain your unit vectors, but for your coefficients, you're going to make the scalar product in this form. Now, vector A magnitude can be done as the square root of A dot A is going to be equal to sum over A sub I complex conjugate square root. And that just generalizes the magnitude of a complex number to the magnitude of a complex vector. So yeah, this complex vector where, you know, A equals A1 to AN, A sub I is a complex number. So yeah, this is the key to the scalar product with complex numbers. Okay. Good, so then all the rules are the same. But this one we're gonna have to be careful with when we generalize to function spaces. So far we've been treating everything like just arrows. Okay. Vectors as arrows, those are the ones we've always learned about and used in physics. Okay, so let me consult program here. Okay, we'll use this. I'm gonna write down a whole list of definitions. I just wanna make sure I have the right ones here. With vector spaces, inner product spaces, norms, make sure I've got the right definition here. Okay, good, this'll work. So yeah, this was just review of vectors as arrows. Okay, now we want to write down this big list of vector space axioms, and then we can get to function spaces as vector spaces. So this was supposed to just be the familiar stuff here. Okay. So this next section, well, we'll get a good start on it. So this is called vector spaces. And I have to write down a big list of definitions, inner products, norms. Okay. And I think the linear operators will come later. Okay. So the first example that I just gone over, I'll just reiterate. If we have arrows, as we're gonna call them, x is equal to the sum of a sub I, e sub I, okay. A sub I can be a complex number, e sub 1, just what I had on the board a minute ago, a bunch of zeros, 1 and a bunch of zeros. Okay. So then we're going to look at vector space axioms and extend this. Extend the idea of the arrows to much more general items. Okay, so what we're going to have is a vector space X. So those elements of capital X are vectors. So X, Y, and Z are the elements or vectors. It's over a field. And a field is the set of scalar quantities, the numbers. So I'll just say numbers, lambda, mu, etc. So we've got the vectors, and then we have the Greek letters for the scalars there. And this would be the real numbers, the complex numbers, okay, field. So what we have is basics here. We have zero element, which we'll just call 0. We have an addition law, addition, which we'll use the plus sign for. So 0 is a vector. If we'll add 0 to things. We have addition, so x plus y is also a vector. And we have a scalar multiplication. Scalar multiplication. So lambda times x is a vector. So far, our arrows do this. Okay, there's nothing different or nothing special about this. We take one of our arrows, we can multiply it by 0. We can add 2 of them and they're still arrows. Lambda x is also a vector. We can extend them. And then we have 8 axioms that are satisfied by these things. 1, 2, 3, be able to write them all out. 6, 7, 8. And we have commutativity of addition, so x plus y, y plus x. we have associativity, so x plus y plus z equals x plus y plus z. Identity for addition, which would be, x plus 0 is equal to x. We have an additive inverse. So x plus negative x equals 0. So the additive inverse says if you have the vector x, it also has its negative multiplied by negative 1. Add them up, get 0, which is that 0 element. 5, the identity for scalar multiplication, which we'll call 1, for scalar multiplication. And so we'll have 1 times x equals x. And then we'll have scalar multiplication associativity. Lambda mu, actually, yeah, lambda mu times x is equal to lambda mu times x. And we have two distributive laws. The first distributivity law is lambda x plus y equals lambda x plus lambda y. And finally, the multiple. The second one is lambda plus mu x equals lambda x plus mu times x. So if you have any set of objects that have these elements and satisfy these rules, then you have a vector space. So, like I said, these have been extracted from the arrows, so they definitely hold true for our ordered pairs, our ordered triples, our ordered n-tuples. You can see they're also going to hold true if these are complex numbers. So yeah, if you just go through these, they seem to contain nothing new. Okay? But those are the things that have to be satisfied by some more general objects. So I'm going to put down the inner product as well. So this would be a vector space. Okay? The next thing is going to be an inner product space. So what we have to do, it's actually kind of implied up here, but the vector space axiom started here. This was just one of the examples. So if we just have these properties, we have to add some to have an inner product space, and that inner product is what we've learned as the dot product. So I'll put down the inner product space axioms. Inner product space. So on the inner product space, and it's going to be our vector space we just had before, there's an inner product which takes two vectors in the left and right side of this thing here. So you take something from x, something else from x, and you map it on to your field. So from our examples in the past, we just take a vector and another vector and map it onto a number. Right? A real number or a complex number. These are the axioms for the inner product. So if you take these two, a vector x and a vector y, and if you reverse their order, you get a complex conjugate of the first one. Okay? So if you happen to have a real vector space, you can just reverse the order and nothing happens. If you have a complex vector space, and if it's the general case, you have to take the complex conjugate with the reversed order. The second property is x lambda y plus mu z. So it's gonna be lambda xy plus mu xz. So again, if these were all real numbers, or the standard inner product, this would, or the standard dot product, this would simply be fulfilled. Okay? It's linear in the right side here. But because of this property, you can't do the same thing for the left side. Okay? Those are the rules. And the third rule is the inner product of a vector with itself is greater than or equal to 0. So it's real and positive. And inner product with itself is only equal to 0 if x is equal to 0. Okay. So yeah, make sure we have all 8 of these. I'm not going to write them down again, but we'll refer to them here and there occasionally. Okay. So the example will do the complex inner product that we saw before. And I think I have to reverse the order to satisfy this set of axioms. So we're going to take A1 to AN, B, B1 to BN. Yeah, we're going to define A dot B as sum over, yeah, I see I had it backwards on the other one. We're gonna go A sub I star, B sub I. Because we're gonna have to have that in order to fulfill this form of the axioms. Yeah, you know, you could reverse the definition in your notes for consistency. It's possible to set them up either way, but this is the formulas we're gonna use. So I had it backwards before. As far as the magnitude goes, it gives you the same thing. So yeah, this, we could have said, you know, A, before we were using the arrows, right? We could have said A, B equals this, right? A sub I star, B sub I. So now if we do, so B, A is going to be sum over A sub I star, B sub I star the whole thing. And that means you complex conjugate each of these individuals. So that'll be the sum of A sub I star, B sub I, complex conjugate. See, and that'll give us B sub I, A sub I star, right? In keeping with the definition there. So yeah, that takes care of that for our complex arrows if we wanted to look at them that way. This is where we'll stop. I'll just put here next. So next in line here would be to talk about the magnitude, okay? So magnitude of a vector turns into what we call the norm. So the norm has its property. We'll start with that next time. So where we're headed with this, as long as you're just doing arrows, you know, this complex thing is important. Or what we're headed to is treating these x and y as actual functions. And then the inner product, we'll have function spaces, and then we'll pick up everything we learned about Fourier series. So that's where this is going. A couple more steps, and then we'll return to our Fourier series and have those as an inner product space. Good, so we'll do that on Tuesday. That's how we segue from arrows to
vector spaces over here, from what I can recall.
yeah, this should make it all make sense.